So far we've talked about just ratio measures of disease frequency. Now I want to talk about differences in disease frequency measures. And these are equally important, but they have a different purpose, as I'll explain. So difference measures usually involve subtracting the disease rate among the unexposed group from the disease rate among the exposed group. And the calculation is very straightforward, provided you have a sort of a measure of prevalence or cumulative incidence or incidence rate in both exposed and unexposed groups. Then you simply subtract one from the other, and then you look to see what the difference is. And so if the risk difference is 0, then there is no association between the two. In other words, if it's 0, then the risk is exactly the same in the two groups. If it's greater than 0, then the exposure is associated with a higher risk, and if it's less than 0, then the exposure is associated with a lower risk, in which case there may be some sort of protective relationship. But the calculation is very straightforward. So the difference is that between this, the difference, and the ratio measure is the difference is a measure of the absolute difference, or the absolute effect of the exposure on the disease occurrence, as you might say. And let me illustrate this by with this example of women who are divided into those with and without hypertension, and those who have and those who don't have a non-fatal heart attack. And so you can see that you can calculate the cumulative incidence in the hypertensive group, 117 divided by 13,422, and you can calculate the corresponding incidence in the non-hypertensive group, 125 non-fatal heart attacks divided by 106,000 person years. Subtract one from the other, and the difference here is 0.00755, or 755 per 100,000 people. So the interpretation of this is that potentially, if you could eliminate the hypertension, you could potentially eliminate 755 cases of non-fatal heart attack per 100,000 hypertensive women. Per 100,000 hypertensive women, not just women in the general population, if hypertension were successfully treated. Now, I have to add this caveat here that this assumes that hypertension does indeed cause non-fatal heart attacks. The caveat is there because of the possibility of confounding by some other factor. So we haven't dealt with confounding yet, but I just make that note there to bear it in mind for future reference. Okay, so let's talk about the differences between the relative risk and the risk difference. So for this purpose I'm using smoking data, and we're going to look at lung cancer and coronary heart disease, both of which of course are caused by smoking. So we have a population of smokers and non-smokers, and so we can look at the mortality rates for both lung cancer and coronary heart disease. So for just starting with lung cancer, for smokers the mortality rate per 100,000 people is about 140, and for non-smokers about 10. So and then we can look at coronary heart disease, and we can see that the difference between smokers have a coronary heart disease rate per 100,000 of 669 and 413 in non-smokers. So let's look now at measures of effect or measures of association. The relative risk, we look first at lung cancer, is 14. So 140 divided by 10, 14. That's pretty high. Now if we look at coronary heart disease, we divide that by that, we see the relative risk is 1.6. So you might say, well, we should be much less worried about coronary heart disease than we should be about lung cancer. However, if we look at the risk difference, in other words, we subtract, instead of dividing one by the other, we subtract one from the other. So 140 minus 10 is 130 for 100,000 years, and 669 minus 413 is 256 per 100,000 years. So if we look at it, we compare these two values, sort of 256 versus 130 per 100,000 person years, and we can see that in fact the potential mortality prevented from by eliminating smoking is much greater for coronary heart disease than it is for lung cancer. Even though lung cancer has the highest relative risk estimate, and of course which often attracts a lot of attention, but in fact the benefits of preventing smoking are much more likely to be found, twice as much in fact, in terms of prevention of coronary heart disease. So this I think illustrates quite well the difference. So the risk difference really gives us a measure of the impact on the population. It really shows that in this case that we get much more benefit, twice as much benefit from prevention of coronary heart disease than from lung cancer. So relative risk and risk difference, they show two completely different things. So we sometimes say that the relative risk is a measure of the strength of the association. So this is very useful when we are assessing the likelihood of causal relationships between exposures and disease, or etiologic investigation, or an etiologic investigation we often say. Now the risk difference really is more important for public health policy purposes very often, because it gives a measure of the potential for prevention of disease in the exposed group. So at this stage we're only talking about prevention of disease in the exposed group by eliminating if you like, the background level of the disease from the exposed group, which leaves you with the amount of the disease which can be attributed to the exposure which we're interested in. However, the risk difference, as we've just been talking about, is really it's a measure of the benefits in the exposed group, but not in the whole population. And we may want to consider this measure of population risk or population rate difference. And this takes into account the proportion of the people who are exposed in the population, for example, the proportion of smokers in a population. And so it gives a measure of the benefits to the population as a whole from eliminating or reducing the exposure in the population. So the population risk difference can be particularly useful to policymakers if they're comparing two exposures and they want to decide where to focus their public health funding for prevention purposes, and you can calculate, knowing the proportions of the exposed to the different exposures in the population, they can calculate the benefits of reducing one or the other, and so you can work out where to put their money and prioritize exposure or prevention measures. So the population risk difference can be calculated, a bit more complicated than just calculating the risk or rate difference, and there are two formulae which are completely equivalent. So the population risk difference can be calculated by multiplying the risk difference by the proportion of people exposed in the population, such as the population proportion of smokers, for example. The second way of calculating it is to take the risk for the total population and subtract from that the risk in the unexposed population. I say risk, but it could be rate too. So these two formulae, 1 and 2, are exactly equivalent. So here I've derived one formula from the other. I won't spend any time on this, but for those of you who are interested in the algebra, you can just follow this through and you can see how we can move from one formula for calculating the population risk difference and subtracting the risk in the unexposed from the risk in the total population. You work your way through and you'll come out with the other formula, multiplying the risk difference by the proportion of the population exposed. So let's apply that to our data that we've already seen for the association between hypertension and non-fatal heart attack in women. So here we have the risk difference. So this, we showed how to calculate this before, and we multiply that by the proportion of the population exposed. So we obtain that from the total column in our 2x2 table. So the row totals and the grand total, gives us the proportion in the total population who are exposed, in other words, who have hypertension. So we multiply that by that, and we get an estimate of 85 per 100,000 people. So this is the number of people in the population who would be spared from a non-fatal heart attack if hypertension could be completely eliminated. And we also show how, using the second formula, subtracting the risk in the unexposed from the total risk, and you can see it comes out with exactly the same figure. Exactly the same figure. So, as my previous slide showed, the two formulae are completely equivalent. Doesn't matter which one you use, may depend on which data you have available. So, so again, the bottom line is that potentially, if hypertension were eliminated, 85 cases of non-fatal heart attacks could be eliminated per 100,000. Really, it should be women in the total population. So the thing about the population difference is that it's dependent on the prevalence of the exposure in the population. So, and so maybe the situation, you may have a very strong risk factor, but if it's only a few people in the population are exposed, then you may have more to gain by eliminating a weak risk factor for the same disease, if it's widespread in the population. So an example of that would be passive smoking and asbestos. So we know that asbestos is a very strong cause of lung cancer in the exposed population, whereas passive smoking, second-hand smoke from smokers, it's a relatively weak risk factor in the population. However, a large proportion of the population are exposed to passive smoking, whereas only a very small proportion of the population are exposed to asbestos. And I'm talking about general populations here, of course. So a lot more health could be gained by eliminating passive smoking across the population than, say, preventing exposure to asbestos in a relatively small proportion of people.